So, when ionic compounds dissolve, it's different than when polar covalents dissolve in some ways, but similar in other ways. So, I don't know, name an ionic compound that we might want to dissolve in some water.
NaCl.
Okay, NaCl are friendly ionic compounds, so let's see, we've got NaCl, NaCl, drawing skills. That didn't work. Something else should definitely have to draw, always. Maybe I should take my search points next. Okay. So, NAs are positive ions, a 1 plus ion, right? CLs are 1 minus ions. And when you have sodium chloride, table salt, you have a nice lattice. They build a little crystal lattice in their solid form, like this. When you put that into water, and water is what kind of solvent?
Polar covalent.
Polar covalent. So, H2O. So we've got, let's see, we've got 2 little H's. And no bonds. And oxygen will have the delta negative end because it's the most electronegative. Well, they're not really fully positive, they're just, this is a partially positive end. The hydrogen gets its electrons kind of stolen by the oxygen. So when we've got a polar covalent solvent, we've got an ionic compound to dissolve, it's the solute. What happens is, like right here, there would have been a chlorine, which breaks away as our Cl minus ion. And the reason that it dissolves is it is more attracted to it's more attracted to the several partially positive ends of water than it is to its own compound. So we've got a bunch of little pluses here, right? That's plenty of attraction to surround it. So then it's going to break off a little sodium ion here, which would be smaller than that, I guess. And the water surrounds it with the oxygen ends. And remember, this is all three-dimensional in a liquid, right? It's not just in the flat plane of the board. So all the partially negatives surround here. You might want to be able to make a similar drawing to this on the test, just in case. Alright, so when ionics dissolve, each negative ion is surrounded by the polar covalent's partially positive end, and each positive ion is surrounded by the polar covalent solvent's partially negative end. And so just pieces are broken off. And remember, matter's lazy. Everything happens because it lowers the net energy. So this is energetically more stable, lower energy kind of situation than this at a given temperature. And we know that temperature affects dissolving, of course, and we'll talk about that in a minute. So, yes, we'll label ionic, dissolves, well, this is what they call solute, and polar covalent solvent. Alright, so another situation we might see, oh, that marker works, is Lily.
So I can we take that some pictures?
We don't have a tissue box?
Yeah, I was looking for them.
That's sad. You might have to get a new tissue box. Cindy, make a note. Bring tissue box.
I'm always prepared.
Oh, good for you.
I'll just
I'll just try to get
Okay.
some. Oh, will you get some paper towels to bring back? Thanks. Then when I get the mess next, we'll have it. So, what is the other option if that will dissolve in a polar covalent solvent? Ionics dissolve in a polar covalent solvent. What else dissolves? Polar covalents. So, polar covalent solute. Okay, so we've got, for ionic, sodium chloride is always our favorite example. For polar covalent solvents, water is our favorite example. But how about a polar covalent solute? What can we use for that? They're far less common in our everyday life.
You could use pH 3 like the book gave you.
pH 3 or NH 3 are good examples. So, let's see. If we have, it's hard to find one that's a solid, like salt at room temperature. But if we have pH 3, for example, that molecule is what kind of shape? Like by Druitt's Lewis structure in 3 dimensions, what would I have? Because it's got reddish hydrogen. Well, I guess I could put the 3 here and a hydrogen here, and it's dashy hydrogen here, and the unshared pair there, which of course takes up a lot of space and forces everybody down. So we've got a pyramidal shape. What was the bond angle on that? 107. So if we have these guys, and they are all trying to be dissolved into a polar covalent solvent like water. All right, so we've got our polar covalent example here. We pick pH 3, which is pyramidal. What color did I make water over here? We'll keep it the same. So we've got water. We've got its partially positive end, and its partially negative end. That is so not it. Okay. So, which end of pH 3 do you think would be the partial positive that makes it polar, which end partial negative? So what's more electronegative, the phosphorus or the hydrogen?
The phosphorus.
The phosphorus is more electronegative, because remember, electronegativity increases the fast charge. Fluorine's the most electronegative thing. Phosphorus is more electronegative than hydrogen. So when we're looking at pH 3, this is going to be our partially negative end. The hydrogen end is going to be that partially positive end. So it's very similar. The only difference is when you're dissolving an ionic, it literally breaks into 2 ions, a fully negative ion and a fully positive ion that gets surrounded by the polar solvent. In this case, these are covalent bonds. They do not break apart, right? This breaks into 2 ions, a sodium and a chlorine. This does not break into ions. It stays a pH 3, but its partially negative end is going to hang out near the partially positive end of water, like that. And just for the sake of ease, I'm not drawing any wedges here. And then the partially negative end, of course, would be attracted to the positive end of water. The partially positive end down here by the hydrogen is going to be attracted to the partially negative end. So we'll put an oxygen there. Too many markers. Okay. So there's the water. There's the water. And then, so now we've got that one's surrounded. And you can see the hydrogen end of water is attracted to the phosphorus end of pH 3. The oxygen end of water is attracted to the hydrogen end of pH 3 because they're opposite charges. This is a lower energy state than this remaining undissolved sitting near the water. The phosphorus end can get extra, or the little hydrogens here on water get extra amount of feeling like they're near electrons when they're near this phosphorus. So that makes it energetically favorable. The one for extra back still. So, dissolving. Polar covalents dissolve in polar solvents. Ionics dissolve in polar solvents, and that's how your book tells you. I note that it's not telling you how to dissolve nonpolar things in nonpolar things. And even if you do some research on that, you're really not going to get some good answers. Nobody wants to tell you about that. So maybe I'll tell you next week if we have time. But so far, there are ionic compounds, though, that do not readily dissolve in water, for example. And they are insoluble, we say, or slightly soluble for some. People get kidney stones, for example, because sodium oxalate, calcium oxalate, like oxalate compounds, some of them are less soluble in water than one might hope. So if you eat lots of things that contain oxalates, like spinach, and you eat lots of things that contain calcium, then you dehydrate yourself, your blood concentration gets a little higher, you get a kidney stone, because there comes a point when calcium oxalate, all the calcium ions floating around in your blood and the oxalate ions floating around in your blood, when they reach a certain concentration, your blood cannot dissolve anymore, and then they come out of solution, form a solid, trapped in your kidney stone. And what is it called when a solid comes out of solution?
Sorry, can you repeat again?
When something comes out of solution. If you're not part of the solution, you're part of the precipitate. Bad chemistry joke. If you're not part of the solution, you're part of the precipitate. So calcium oxalate will precipitate out of your blood at a certain concentration. Keeping yourself well hydrated helps to prevent that, and then you don't get a kidney stone. Please remember, don't get a kidney stone. So, dissolving is not some things. Dissolving is not melting. I mean, little kids say, oh, you put the sugar in the tea and it melted. Nope, sugar melts at a really high temperature and your tea is not that hot. Dissolving is not melting. The solid solute did not become a liquid. It is still a solid, it just dissolved. You have to reach a certain temperature for something to melt, and dissolving is not that. It just goes from a solid to an aqueous form, but it's not melted into a liquid. Dissolving is also not a chemical reaction. We talked a lot about physical changes at the beginning of the year, and dissolving is a physical change. You can undissolve something pretty easily by evaporating the solvent off, or filtering out, or you have to have something better than a coffee filter, but it is possible. But you can reverse dissolving because it's just a physical change. Okay, so liquids tend to dissolve in liquids more readily than solids dissolve in liquids because there's already space between liquid molecules, so it's easier for them to dissolve. Solids have this happen where the solvent has to come in and interact with the solute particles and dissolve piece by piece. There are ways to increase the time that it takes, and decrease the time, of course. We'd like to decrease the time it takes to dissolve something. So what are some ways, if we want to dissolve something faster, that we could decrease the time it takes to dissolve?
And then heat the solvents.
Heat the solvent, yes. So why does that decrease? If you picture these drawings, why would heating the solvent decrease the time it takes for the solvent to dissolve?
Because it puts more energy into solvents, making them bounce around more, so there's more space.
And not just space. So this is the kinetic theory of matter. Did we read that this week? Oh, we're going to talk about it anyway. So it's really important for solution making to think of how you're going to increase your rate. You can also increase your amount, which we'll talk about, remind me. But increasing rate. So if my solvent particles are hotter, they're moving faster, right? Then you tend to have more opportunity for them to interact, right? If they're moving faster, they're going to have more collisions, more interaction between the solvent and the solute, right? So dissolving happens faster when more free water molecules come into contact with the solute and then can interact and dissolve it, carry it away, surround it. What else could you do to increase the number of interactions between the solvent and the solute besides heating?
Put more solvent in.
Okay, so yes, that might increase. It might actually not, too. Heating is the best way, absolutely, to do it. Okay, so you're dissolving sugar in your iced tea. What do? Stir. Stirring. That stirring is a great way to increase the number of collisions and interactions between your solid, solute, and your solvent. You stir, you're going to make more of the solvent molecules hit the solute ions or molecules, and that increases the rate of dissolving. Anything else you can do?
Oh, no, not with ice tea. I was thinking with the gas.
Well, you could. You guys are too young to have used a lot of sugar cubes, but what's going to dissolve faster, like table sugar like we use or sugar cubes? Why?
The molecules aren't
Because-
close together.
Okay, so surface area is a big deal in dissolving. Okay, a sugar cube has only so much surface area, but there's a whole bunch of sugar that's not on the outside that the molecules can't even interact with until some of it gets put away. But when you just have a flat layer of sugar on the bottom, there's a large surface area for amount of sugar that the molecules can crash into and hopefully dissolve some of. So crushing, basically. You crush that sugar cube, it's going to dissolve faster, but it's not going to be as cute. So stirring, crushing, and heating the solvent are the best ways to increase the rate of dissolving. And that works with any type of solution that you're making. Those things, stirring and crushing, don't increase the amount of solute that will dissolve into your solvent. They only increase the rate at which it dissolves. But we all know that there comes a point when your solution is saturated. It cannot hold more solute for the amount of solvent that you have, right? Like Jenny tests this out every time she makes tea, I think. How much sugar will this tea hold?
Yay!
But there comes a point when there's just going to be sugar laying on the bottom of that cup because it's not going to dissolve anymore.
It's still edible.
Ugh. Yeah. But how could Jenny get more sugar to dissolve in her tea? Not just faster dissolving, because crushing, stirring, and heating make the dissolving happen faster. But how can you get more more solute to dissolve in your solvent?
So you get more
So,
solvent.
yes, but it wouldn't increase the concentration. We're literally trying to get more in the same amount of solvent.
You heat it up.
Heating. So heating not only increases the rate of dissolving, but heating your solvent almost always also increases the amount of solute you can get in your solvent.
So it increases the solubility?
Yes. So almost all ionic compounds and mostly polar covalent compounds, you can dissolve more solute. You can make a more concentrated, saturated solution when you heat the solvent. So, and I think the example they gave in your book was a hot tub example, where if you do your hot tub chemicals right, at the normal temperature for a hot tub, you're gonna have a nice, clear, happy hot tub. If your hot tub gets cooler, your saturated solution of germ-killing salts will precipitate, because at a cooler temperature, the hot tub water can't hold as much solute. So it comes out of solution, and then you have cloudy water, because there are solids kicking around in that water. If you bring the temperature back up, it redissolves and you're all good. So if it comes back up to temperature and doesn't redissolve, you have a problem with your hot tub. You need to do something. Hot tub, I have a degree in chemistry, and I can keep a pool just fine, but hot tubs, I can't keep them happy and safe. I can't keep a saltwater tank either, a fish. It's very complicated. So, and if you do want to keep a saltwater fish tank, solution chemistry is hugely important for you.
What about a saltwater swimming pool?
I've never tried. I only had a
We have
chlorinated swimming pool.
I say it's hard to keep up with just because of all the factors. Yeah.
Yes, I bet.
Yeah, my dad does it also on the. We just know it's easier on our eyes when we go swimming.
Yes,
Because my
I'm
brother's,
sure.
Isaac gets really, really red on the eyes when he goes swimming for me. So.
Ginger does too, and his skin gets weird. So saltwater is probably a better way to go. But, I mean, it is highly affected by temperature and algae growth, and, you know, there are lots of things that like to live in saltwater, so. But solution chemistry, I mean, I'm sure as the pool temperature changes, you find a lot of changes to how much stuff dissolves. Now, table salt, sodium chloride, is not as affected. So when you heat water, more salt does in fact dissolve, but not dramatically more. Other ionic compounds like potassium chloride have a much sharper solubility curve. So table salt's like this. Like you can dissolve this much in cold water and just a little more in hot water. For potassium chloride, it's like dissolve a little bit in cold water and a whole lot in hot water.
Same thing with Epsom salt.
I bet.
Found that out.
What did you use it in?
We just boiled water and tried to saturate the solution, and then all of a sudden it just turned like sludge.
Yes.
Just like that. I was like,
Precipitation. I'm actually going to try that next week with potassium chloride. Epsom salt is magnesium sulfate.
Next class.
Next. Yeah, not next week. Don't come next week. I'll come, but I won't be here. I can go to study hall. It'll be fine.
Except that you won't be there to open the door.
Yeah, don't come until 8:35 or you won't, get the door opened. So, where am I? Okay, so we talked about solubility, saturated solutions, precipitation. Liquids, dissolving in liquids are not as affected by temperature or pressure. They're generally quite soluble. Many are miscible, so meaning that you can mix any proportion of two liquids, and if they're soluble in each other, they'll be soluble in most proportions. But pressure and temperature don't necessarily affect liquid dissolving in liquid very much. Solids dissolving in liquids are strongly affected by temperature. Gases dissolving in liquids are strongly affected by
pressure.
and temperature, yeah. So when we look at solubility, what are our rules for solids dissolving in liquids? So a solid solute dissolving in a liquid solvent. We just talked about if we increase temperature, what happens to solubility?
Increases.
Then increase solubility. And rate of solution. If we increase stirring in surface area, what happens?
Dissolving rate goes up.
Yeah. But not solubility. Surface area. and that increases just rate, not solubility. So then for, isn't this, for solubility of a gas in a liquid. So what's a good example of a gas dissolved in a liquid that we can all think about?
Carbonate.
Okay, so a soda that's carbonated. And all the time, if you're in a test or something, and the final has a lot of this. Anytime we're talking about solubility of a gas in a liquid, you're thinking about a soda, because that's something we all have lots of experience with. So, if I increase temperature, what happens to solubility of a gas in a
It
liquid?
decreases.
Okay, so that will decrease solubility. And if I increase pressure, what will happen to solubility?
It will go up.
Okay, so with a soda, solubility. Okay, with the soda, you want to keep it cold to keep your gas dissolved, keep it fizzy. You want to keep the lid on, right? High pressure. You don't want to just leave it sitting out with the lid off. You don't want to open it until you're ready to drink it because it keeps it pressurized, right? So both of those increase the amount of gas you can dissolve in a liquid. Oh, just because solution dissolving is a physical change does not mean that there isn't a heat change associated with it. Now, we always say, and especially when we're talking about, is there evidence of a chemical reaction here? Heat change is one big evidence of chemical reaction. But heat change is not always evidence that a chemical reaction occurred all by itself. You guys noticed last week, remember we passed around the, when I dissolved lye in water and the thing got hot? So when you dissolve something and heat is given off, does anyone know what that's called?
Exothermic.
Exothermic. And it's not a reaction, so I can't say exothermic reaction. But it's an exothermic process. When you dissolve something, heat is given off. And when I dissolve something and it gets cold because it needs to take in heat from its environment, what's that called?
Endothermic.
Endothermic. And for when you took biology last year, that's like cold-blooded animals are ectothermic. Yes?
Yeah, I think so.
Ectothermic.
Yeah, it sounds
So
like that.